Hello everyone. In this video we are going to talk about 2D solid mechanics problems. In the previous video you saw me talking about 2D steady state heat transfer problems using triangular and rectangular elements. So what we're going to do today is we're going to first talk about torsion problems and then this plane stress problems. So let's get to the torsion problem. So in torsion, the governing differential equation based on the Prandtl formulation, if I pronounce the name correctly, is the second derivative of the stress function phi with respect to x and plus the second derivative with respect to y plus 2g theta equals 0, where g is the shear modulus and theta is the angle of twist per unit length. And if you look at this equation, this is the exact same thing as the equation we had for the heat transfer, right? Do you remember it was the second derivative of temperature in the x and y direction added together, but each one was multiplied by a kx and a ky. Here we don't. What we need is to set those k's equal to 1 and replace phi by t. And then the homogeneous term over there was the q dot term. Here is 2g theta. So if we replace those and do this a simple replacement, the results we had over there for, let's say, a triangular or rectangular element, we can exactly have here for torsion, okay? So we don't need to rederive all of those, let's say, conductance matrix that we had, and then the thermal load here. We can have the stiffness matrix and the mechanical load by basically copying and pasting those equations, just replacing the corresponding entities. So here, for rectangular element with length L and width W, then the stiffness matrix is going to be some of the terms that we have for the x and y direction here, and then the load due to torsion is going to be 2g theta a, where a is the area of the element under twist or torsion over 4 1 1 1 1, and then the shear stress for the element or on the element Tzx or tau zx, which is the partial derivative of the stress function in the y direction with respect to y direction, is going to be partial of y of phi. Now here we're going to write phi as what? As the linear combination of the nodal values of phi at the four nodes I, j, m, and n, and the dot product of that vector with the shape function vector, which is si, sj, sm, and sn. And here we assume we are using the linear linear element and the shape functions that we saw last time, right? Which are based on the x and the y, right? So we had all of this in my previous lecture. So what we need here is the phi's are constant values, so we need to take y derivative out of the s functions. And the y derivative out of the s functions are these guys that you can see, right? So for example, this one here, the element, if you remember, it was like x over L and y over W, right? And there was a negative. So if you take derivative of this term, with respect to y, it's going to be negative 1 over LWX, or LW over 1 over LW times negative x, which you can see basically here, right? So those elements that you had for the SI, SJ, SM, and SN, if you take y derivatives out of them, you get these four components that you can see here, and they all share a 1 over LW, so I factored it out for you here, right? So this times the nodal values of phi I to phi n, that is going to give you the shear stress tau zx. Similarly, tau zy is negative derivative of the stress function with respect to x. So now you have to take x derivative of those This time these guys are going to be functions of y, each one of them. They all again share a negative 1 over LW, and then again multiply by the phi's to get what? To get your shear stress. So these results are all for what? For a linear rectangular element, okay? The distribution of shear stress as well as the stiffness matrix, the rotational stiffness matrix, or torsional, and the torsional nodal load, or elemental load, basically. Similarly, we can go ahead and use the results we had for thermal, conduction, convection, heat problems, heat transfer problems, and bring them here and use them for the triangular element. So again, the stiffness matrix is going to be some of these two terms here. And the definitions of beta and delta is exactly like the previous time. Okay, so there is no difference in definition of beta and delta. And this is the, again, elemental load, and then the tau zx and tau zy. This time they are going to be based on the nodal values of phi as well as the delta values and the beta values. And I added here for you, for the sake of completeness of the material, I added the formulas for betas and deltas right above here, so you can have them all in one place. Now let's look at one example using these matrices. So here we have this bar here, this rectangular or square bar, dimension 1/2 inch by 1/2 inch. It is made of steel with G of 11 kilo KSIs, right? And theta is 5,000 of radian. And you want to find the shear stress distribution within the bar. And here the problem is again perfectly symmetric. So what I can do is, instead of looking at the whole square, I can only look at 1/8 of that. And here you can see that the portion I have chosen is this area here. So this area is 1/8 of the whole cross section that I chose to analyze, and you can see that here. And the shape of it requires that I use one square element and two triangular elements here. So we call the triangular elements 1 and 3, the square one 2, and we call the nodes 1, 2, 3, 4, 5, and then 6 here. So first, for the triangular elements, if you look at them, since the x's and the y's are measured in terms of the local coordinate here, so the values that you get for beta and you get for delta, they are going to be basically the same for elements 1 and 3, right? Because their dimensions is the same, the orientations are the same. So the betas and the deltas you get for both of the elements as well as the areas, they're all the same. Therefore, the K for both of these elements is going to be the same. The only difference is the nodes involved, which for one of them is 1, 2, and 4, as you can see again, and the order matters. And the other one is 4, 5, and 6, which you can see here. Other than that, the numbers are exactly the same. For element 2, it's a square, and again we have the formula for the square element, which is this guy here, and we plug it in the values of W and L, which in this case, remember that the whole thing is 1/2 inch, so this from 1 to 3 is a 1/4 inch, and then from 1 to 2 is simply, each one of these dimensions here is 1/8 inch, okay? So, or 0.125. Therefore, we can get our element 2 stiffness matrix, and again, the order is going from 2 to 3 to 5 to 4, as you can see in this order here, counterclockwise. So once I have those K's of elements 1, 2, and 3, I can assemble them together and get my global K matrix, as you can see here. And then I can go and look at the nodal, the elemental loads. So for the triangular one, we have elements 1 and 3. And for the square one, we have this one here, right? For the square elements. And again, we have the formulas for them. So this is the formula for element that is triangular. This is the one for the one that is square. And the parameters that you need is G, theta, and A. And we have all of those information for each one of the elements 1, 2, and 3. Therefore, you can see that f of 1 and 3 again are exactly the same. F of 2 is different. And then you can basically assemble those f1, 2, and 3 together and get f global. And then basically you say that k times phi equals f, right? Where f is f of global and phi is the unknown matrix. The matrix of unknowns, and k is again k of global here. So that gives you 6 equations, but you don't have 6 unknowns in this case. The phi's, if you look at them, if you're just after the phi's, you don't have really 6 unknown phi's. Only 3 of them are unknown. Which ones? Only 1, 2, and basically 4, I assume. Let's take a look at the walls here. So if you look, 3, 5, and 6 are the unknown ones, the known ones, and 1, 2, and 4 are the unknown ones. Why? Because if you look, 3, 5, and 6 are on the free edge. They are here, okay? They are on this area, which is the free edge, and on this free edge, basically there is no stress. So over that free edge, phi is 0. So phi is 0 for 3, 5, and 6. These are the boundary conditions. Therefore, here I assume there is a mistake here in the textbook. This guy should be phi of 4, not phi of 3. And so now I only use the information for 1, 2, and 4, right? Which basically involves columns 1 to 4 and rows 1 to 4. So you only basically need this part, and then here, and then here. So if you put them, you should be getting this matrix times phi of 1 to 4 equals, in here you only need this one, and this one, which you can see. That gives you phi of 1, 2, and 4. And now you have all of the phi's. You have the stress function at all 6 nodes. But that's not what we want. What we want is to find the stress distribution. So now we have to find tau zx and tau zy, okay, for each element, and what kind of function they give you, because we are after stress distribution. So we want a function for the stress, whether it's tau xz or tau yz, we need a function. Now we have formulas here for them that I offered to you. So tau zx, as you can see, these are deltas times phi's. Tau zy is negative betas times phi. But what's the problem? The phi's are all constants, and deltas and betas are also constants in this case. Therefore, the taus are going to be constant numbers, as you can see down here. So tau zx and tau zy for element 1, they're going to be negative 11 and 14 psi's. And then for element 3, they're going to be 0 and they're going to be 26 psi's. And what's wrong with this? The wrong part is that inside this triangular element, the shear stress is not constant, okay? We know that if it was a circle, the shear stress depends on the radial distance from the center. So as you get away from the center, the shear stress does change. And here, going from 1 to 2, your radial distance does change from the axis, right? The axis here is at origin. Therefore, the shear stress at point 1 and 2 should not be the same, right? There should be a distribution of a stress on this element 1, 2, and the same for on element 1 and then on element 3. But when you use a linear triangular element, what's wrong with that? It gives you constant stress distribution inside it. So ideally, the triangular element is not what? Is not really a good idea for shear stress distributions and the torsion problems. If you have to use a triangle like this, you better at least use which type? The quadratic one, which had basically nodes in the middle of the edges as well. That one should give you a function instead of a constant number, okay? For the square element, for the rectangular element, we don't have that problem because remember here that these shape functions that are multiplied by phi's, they are functions really. Therefore, when we plug in, right, and simplify, here at the end of the day, you get a functions of x, and here you get a function of y. So it shows that the stress distributions, tau z x and tau z y, they depend on the location. They are not constants. So a rectangular element is good, but if you have to use a triangle, make sure you use a higher order triangle. Okay, and for that you have to derive the k, and you have to derive what? The tau formulas and the f, which is not provided in this video. You can look it up online, okay, because you cannot find it also in this textbook. But you should be able to either look it up, or you should go with basically the same procedure here and you derive it yourself, okay? So I can leave it up to you as a practice so you can derive it. So this is the torsion problems, right? So two-dimensional. The second type of problems that we're going to look at is plane stress problems. So for plane stress problems, we only have three elements, and let's assume the plane is xy plane. So we only have sigma xx, sigma yy, and tau xy or yx, which are the same. And the element I'm going to be using is the triangular element here, okay? And the reason for that is the formulas for them are a little bit smaller. For the triangular element, the matrices involved are much larger, and you don't have basically any nice closed form formula. The integration involved in that, you have to do it numerically. So you won't get any closed form formula for the matrices and so on. So here we just focus on the simpler form, which is triangular. The first thing you need to do, because we're going to ultimately use the minimal potential energy formulation, you need to find the stress and the strain and plug them into the strain energy, and then relate that ultimately to the U, okay? If you can relate that, the strain energy ultimately to the nodal displacements, then the coefficient that you will find, this guy here, will be your stiffness matrix. So what I need to find is to relate my stress and strain to displacements. How? So the first thing you need to do is you assume that at each node, right, this is a 2D problem, so each node that you have is going to have two motions, an X motion and a Y motion. So node I has two motions, node J has two motions, and node K has two motions, okay? And we call these motions what? We call them U and V, right? Or in general, you might call them anything else, but in this textbook, we call them U and V. So horizontal displacement U, vertical displacement V. And the way that we approximate these fields for U and V, because in general, your U and V should be functions of X and Y. Okay, so they are like this. So how do we approximate these two-dimensional functions? Well, here we say the nodal values, the X displacement values at the nodes times three shape functions are going to approximate my U, and then the vertical displacement at the nodes times the exact same three shape functions will give me what? V. Okay, and these shape functions Si, Sj, and Sk are the exact same thing that we had in what? We had them in 2D problems in the previous case and previous video. And let me show you those in case you forgot. And these are those shape functions here, right? For a triangular element based on the alphas, betas, and gammas. Okay, so these are those shape functions that we had. And now what we need, as I said, is to find the strain and the stress vectors in terms of these S's and U's and their derivatives. So how do we do that? Well, the elements of the strain are normal strain epsilon xx, epsilon yy, and gamma xy. So epsilon xx, based on what we know from solid mechanics, is partial derivative of horizontal displacement u with respect to the horizontal axis x. And if you take x derivative from this, the u's are going to stay because they're constant numbers, so you're practically taking derivatives of si, sj, and sk with respect to x, which they're going to be the beta parameters over 2a. So this is your epsilon xx. Epsilon yy is partial derivative of vertical displacement with respect to the y direction. So it's going to be based on deltas and u's. And deltas are y derivatives of the s functions. And gamma xy, basically the shear strain is partial of u with respect to y plus partial of v with respect to x, which involves both deltas and betas as well as all of the u's, horizontal and vertical. So we can write our shear strain as a matrix B times the nodal values, where this matrix B is basically all of these coefficients of u's, which are betas and deltas, and of course they all share 1 over 2a. So that's the relation for epsilon. Also, stress sigma is related to epsilon through the Poisson's ratio and the Young modulus. So we can write sigmas in terms of epsilons. So if we define all of these nus and e over 1 minus nu squared, if we define them as a matrix and call it the nu matrix, then sigma can be written as nu times epsilon. So now we're going to plug them in here. So sigma transpose is going to be transpose of nu times e times epsilon. So the transpose changes the order. So it's going to be epsilon transpose nu transpose. And then epsilon transpose, and now epsilon itself is b times u. So if you plug that in here, then our total strain energy is going to be what you can see down here. And here u and u transpose can be brought out of the integration because they don't depend on the element. So if you bring it out, then you can write it as basically 1/2 u transpose that integral times u, and that integral is basically b transpose times nu times b integral over the volume. Okay, and so this term here is gonna be your k, and since b's are constant and nu's are constant, if you bring them out of the integral of dv is going to be the volume. So this v, capital V here, is volume of the element, and b and nu are defined up here. Okay, so if you multiply them together, you're going to get this constant matrix of k, which is the stiffness matrix for 2D stress. And then for the load matrix, depends on whether the load is concentrated or it is distributed. If the load is concentrated, Q, then the components of Q on each one of the nodes, Q, Ix, Iy, Jx, Jy, Kx, and Ky, are gonna form the elemental load, basically. Now, some of them might be zero because your concentrated load is probably not applied on what? On all of the nodes, right? If it's only applied on one of these nodes, then probably only one or two of them are non-zero and the rest of them are zero, okay? So that is in general for a concentrated load. Now, for a distributed load that has components Px and Py, then what we need to do is to basically find the amount of total force. So here what we'll do is we multiply the Px and Py by dA, which is basically because Px and Py in general could be variable, could be constant, and we multiply them by the shape functions and integrate over the area that is formed by each edge. And you might say these are edges, these are not areas, but remember that your element has some thickness. So this element here has a little bit of what? It has a little bit of thickness like this. And its thickness, we call it T. So the area here, when we say dA, we are talking about something like this. Okay? And here we find the basically the effect of that force Px or Py, the component of P on that. It might only have one of them or both of them in general. And if you simplify with this matrix of shape functions and that P and you integrate, then you will have what? You will have one of these three or maybe several of them depending on which edge they are applied. So here we assume that you have both Px and Py both applied to the edge Ik. Therefore, the elemental load is going to be this guy here. T, as I said, the thickness of the element or the thickness of the body, the object, times the length of edge Ik divided by 2 Px, Py, 0, 0, Px, Py. Now, if P is only X or P is only Y, then one of these P's is also 0. And similarly, if it is applied on the node Ij or on the node Jk, then you can find what? You can find similar, basically, matrices for them that you can see over here or over here. Okay, so these are for distributed load on one of the edges, and this is for what? For concentrated load on the nodes, basically. And this was the matrix that we did not expand, and we just left it as is, as the product of some matrices, but that's going to be a constant matrix. Now let's look at some example here to clarify it for you. So here is one element in an object, and then here we are only looking at one element in a part, and then on this element at node J, we have the load 500 concentrated load at 50 degrees. And then with respect to the horizontal direction, the coordinates of the nodes are given. And on this edge Ik, we have a distributed load in the X direction of 12 megapascal. And then we want to find the global stiffness matrix and the global load matrix for this element. So what we need to do is the coordinates of the points here and find the betas and deltas, which you see we have done. And then we can find the area of the element, which again, based on the coordinates of the nodes, we can do it based on a simple determinant. And now this is your new matrix, which has E in it, right? E here is 200 gigapascal, and nu is 0.32. So you see that is my new matrix. And then in order to form the K, not only we need nu, we also need B's, and B's is all based on betas and deltas, which you can find here. The volume of the element is the area of the element times thickness, and we have the area already here. Of course, it should be half of that because that's 2A, and multiply by thickness, which is 3 mils, so we can get this volume as well, right? And then once we have everything, we can form the stiffness matrix, which is this guy here. Okay? And these six things that you see here, these are UIX, UIY, UJX, UJY, let me write them down here for you. UKX and UKY, all of the nodal displacements that this element has, because it's plane stress, so each node can move in two directions, and there are three nodes, so that's why it's a 6 by 6. And here we have a distributed load and a concentrated load, so we have to use both of these formulas. For the distributed load here, for P of X of 12 meg and Py of 0 here, because there is no Py, and it's applied on IK, so we're going to use this formula here, right? Because this is only on IK, we're going to use that formula. So we need the length of that edge from I to K with thickness over 2 Px and Py. Py is 0, Px is 12. And you need the length of this member, which you can easily find the distance between these 2 points using the basically Pythagorean theorem. And that's what you can see over here. This is the length of that member. And you see P of y is 0. Therefore, this is the elemental load here due to the concentrated load. And then for the distributed load, I'm sorry. And then for the concentrated load, the loads are applied to node J. Therefore, on node I and K, they are 0. And you just need QJX and QJY, which are the components of this 500 with angle 50 degrees, which you can see here. And they are both negative because they are in the negative X and negative Y direction. So this is the elemental load matrix due to the concentrated load. This is the one due to the distributed load, and then you add them together to get what? The global, not the global, the total elemental load matrix for this element. So now that is F, and this is what? K. Now if the part was only the single element, then we needed some boundary condition to determine all of the U's in this case, right? Or find reactions and anything like that. But here is just one element of a giant part, and we are only interested in finding the K and the F for this single element here. Okay, so when it says the thin plate shown below, it's not the whole thin plate. Let me write it for you. For an element inside a thin plate, for the element inside the thin plate shown below, then find those, right? Or you might say, no, this is my entire plate, and then find basically, you need some constraints here, so this guy does not move, and then from there, you can find what? You can find everything else, right? So for example, you can say, let's say, in this case, I have basically fixed this entire edge here, right? That means the degrees of freedom for nodes I and J are 0. So all 4 of these are 0, and all you need is the displacements of K, which you can find basically from the bottom 2 rows of K and the bottom 2 elements of F, right? Or one of these nodes I pivoted, the other one is on a roller or anything, then you can find the reactions for them, you can find the displacements and so on. So hopefully this video was useful to you and you learned how to perform basic plane stress problems using the triangular element, as well as the torsion problems using a combination of rectangular and triangular. And again, one more time, the reason I did not discuss the formulas for K and F of a triangular element is that these integrations that you need to do, okay, here, this guy here, that one is not gonna be super simple for a rectangular one, and the reason for that is for a rectangular one, this B matrix is not gonna be constant. The derivatives of basically your u's and v's, or which are basically the shape functions with respect to x and y, these guys are not going to be constants, betas and deltas. So you're not going to get a constant matrix like this. Nu could be constant, but not beta. So the whole B matrix is not constant, and therefore, when you need to do this integration here, these terms will not get out of the integral. So your K is really not this. Your K is what? Is the integral of B transpose nu B dV. And if this B and B transpose are not constant, you have to perform integrations here. In this case, they are constant. We brought them out. Integral of dV became V. But if these are not constant, then you have to do these integrations here. And we can do it with the Legendre formula that I showed you. But again, it's not going to be as simple, and I recommend you derive it by yourself if you want. Okay, and solve an example on it. If I have time, I'll make a video about that, but in this case, I just wanted to keep the total length of my video short. Thank you so much for your attention. I will see you in the next video.